Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. And Lord, I thank you for these students. Just pray that you just help us to use this time wisely, Lord. And I just pray, Lord, that we again would glorify you in what we do this day, Lord. In your name I pray. Amen. Any questions about anything before I get started? Would you like me to go over the quiz?
Yes.
Yeah. All right. We have a couple minutes today. I can't always do that, but I can do it today. So let's do that. Hopefully there are no mistakes in my solution. Except, of course, for the ones I put in there on purpose to see if you're following along. Come on. Get there. So this quiz was basically half, it was half trig substitution, half partial fractions, which is more or less what happened last week, right? First of all, set up in terms of ABC, blah, 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 blah. Partial fractions decomposition. So basically the point here is this can be factored. That's x minus 2 times x plus 2. Factoring matters. And so there you go. So this gives me x plus 2, x minus 2. The x squared plus 5 gives me the cx plus d over x squared plus 5. And this guy gives me these three characters right here. That is the partial fractions decomposition. There you have it. Any questions? Problem 2, straight up trig substitution. Here we have square root of x squared minus 9 over x. This suggests an x equals 3 secant theta substitution. So that gives me dx is secant tangent, x squared minus 9 is 9 tangent squared. So the square root of x squared minus 9 is 3 tangent theta. Plug these up over in here. Secants cancel. 2 of the 3's cancel. 1 3 is left over. You get 3 tangent squared. But tangent squared is secant squared minus 1. Integral secant squared tangent, integral of minus 1 theta. But multiplied by 3 gives you this. And then I can draw the triangle to figure out substitutions. But it so happens that in the process of doing the algebra, I actually already have the formula I need over here as well. Right? Like 3 tangent theta is the square root of x squared minus 9. So like it's right there. And then this, well, that's a naked theta. I've got no choice but inverse tangent of square root of x squared minus 9 over 3. And there you have it. So I think that's about the best I can do for that one. Again, any questions? No. Here, by the way, that was very much like one of your homework problems, right? I think there was a 1 instead of a 9, but otherwise it's pretty much the same. I think this actually is one of your homework problems. So recommended homework problems, obviously. So let's see, we complete the square downstairs. This gives me that. If I didn't make a mistake, I don't think I did. And then, so that suggests I make a x minus 1 equals root 2 tangent theta substitution. If I do that, then the thing inside the root becomes 2 secant squared theta. And so when I take the square root, I get square root of 2 secant theta from that substitution. Then upstairs, x is a little bit sneaky. You got to solve for x, right? So if x minus 1 is square root of 2 tangent theta, then that means that x is equal to 1 plus root 2 tangent theta, right? Got to do algebra. So I plug that in. The dx, of course, is root 2 secant squared d theta, and then I multiply this stuff out, except the secants cancel, right? Root 2 cancels. I'm just left with 1 plus root 2 tangent theta, secant theta d theta. Multiply this stuff out. You got a secant integral, secant tangent integral. That integrates to secant. This integrates to log secant plus tangent. Then you can convert back to algebraic formulas using the triangle, or the algebra we just did. But there's a root 2 common, so I can rewrite that as minus log of root 2. And I just lump that into my constant C2, and there's a nice answer for this one. As I mentioned here, if you wrote your answer like this, I do want the grader to give you partial credit. You should earn 2.5 out of 4 points if you did this. Sorry, it's a little bit cramped over there, but you get the idea.
What if we didn't pull the 1 over square root?
You lose minus 0.5 points. Assuming the grader follows my instructions. Okay. So here we go. We have this find partial fraction decomposition for this. So we're going to look for a over x minus 2 plus bx plus c over x squared plus 1. So what I did was just to multiply both sides by the denominator, collect like terms, equate coefficients. It gives me 3 equations, 3 unknowns. I add equations, then I multiply an equation, I add them. Eventually I find my way to c equals to 1. Once I know c is equal to 1, that tells me b is equal to 2 by back substituting. And then once I know b is equal to 2, I can go back and find a is equal to 3. There are other ways of doing the algebra, but all roads lead to 3 over x minus 2 plus 2x plus 1 over x squared plus 1. You might notice 3, 2, 1 here. Questions? There's an easier equation, right? I could have plugged in 2. That would have given me like a super nice equation. Like my solution's not the slickest one, right? If I plug in 2 here, what happens? Plug in 2 up here, what do you get? 5 times a equals to what? 20 minus 6 plus 1. 21 minus 6. 21 minus 6 is 15. 15 is equal to 5a. In other words, a is equal to 3. So you could see that pretty easily just looking at the x equals to 2 equation. I just didn't do that this time for the sake of doing some algebra, right? Like, why didn't you do it the easier way? I don't know. Don't ask me. Ask the guy who wrote this. That was me yesterday. That was a different person. So short of time travel, we can't really ask. All right, problem 5. Use the technique of partial fractions to integrate this thing. Now this is a very friendly problem. I hope many of you got this. So the point is that factors to x plus 2 times x plus 1. So the partial fractions is this. But we can work out the a and b by this algebra down here. Now this one just screams plug in minus 2, plug in minus 1, and that gives you b equals minus 1 and a equals 2, just like that. So this is exactly that, which integrates to this. And then you can, if you want to, rewrite it as log of x plus 1 squared divided by x plus 2 plus a constant. I want the grader to give you full credit on either one of those answers in this particular problem because I haven't said anything particularly, fussy about simplifying your answer here. Right. Of course, if you don't like partial fractions, you can also add. You can also be like, x plus 3 is this. That doesn't work. 2 times x plus 2 minus that. Well, that's the same, right? Because I got 2x minus x, which is x. And this gives me 4 minus 1, which is 3. So if you just kind of think about adding and subtracting things, you could come up with this. And then if you just do algebra, that's 2 over x plus 1 minus 1 over x plus 2. So, like I said, clever. But in order to do this, you'd have to see this. Can you see that? Maybe, maybe not. But we have this method up here, right? So if we can't see it, it doesn't matter. We have a method. Sometimes you can see this kind of like sneaky adding 0 thing easier for other examples. This one I think is kind of opaque for that technique. Hard to see through, And then the long division. All right, so integrate this thing, hint long division. So here's my x to the 4th plus 2x cubed plus x squared plus 2x plus 3. I got to divide in x squared plus 1, so I put it here. X squared gives me x to the 4th plus x squared. Subtract. What we're left with is 2x cubed plus 2x plus 3. The x squared and x to the 4th canceled. Then I add 2x. That brings down a 2x cubed plus 2x. These guys cancel. It leaves me with 3. And that's the remainder. So that gives us this lovely bit of algebra over here. So you plug it in and integrate, and bam. That's it. It's not actually that hard, is it? No. And then finally, the hyperbolic problem. I told you to be hyperbolic here. That is to avoid an integral of secant cubed if you go the trigonometric route, right? And so here, complete the square. Then that suggests I make a x plus 2 equals sinh the substitution as we discussed. So x plus 2 squared plus 1 gives you cos squared. So this square root is just a cos theta. Dx is cos theta d theta. I get integral of cos squared. But cos squared can be rewritten as 1/2 cos plus 1 plus cos 2 theta as we discussed. And so that integrates to what's down there. And there's your answer in terms of inverse hyperbolic sine. All right. There is a secret, there's an Easter egg here. There is a hidden bonus point. If you had simplified your answer in this way, you earned a super extra secret bonus point, which I, of course, did not announce because I want to distract you from other things, but there it is. So, as we discussed, you can rewrite the sinh 2 theta as 2 sinh cos, which is this, but, you know, if any of you got that, I'd be impressed. Anybody get it?
What's a super bonus?
It's a hidden bonus point. Like I was told it was an Easter egg. Anyway, any questions? That's pretty much it. Yep. Sure. How far up? This is posted in the Blackboard, of course. I'm gonna turn the lights back on. I have to, otherwise I'll get sleepy. Well, oh, I guess while I have this out, something I don't know, should I? No, I just put it away. I should write things out for you guys. I get lazy, start looking at homework solutions with the projector, then it all falls apart. It's tempting. I shouldn't do it. Helps you guys to see things written. All right, so any questions about anything in particular? I hope that this quiz was like a little bit more reasonable in terms of time, right? If you didn't get something, it's because you didn't understand something, right? I know that because at least 10 of you left early, and I'm assuming not for reasons of desperation. But I'll see when I get the graded ones back. Where are we? 8.6? So what's the deal with 8.6? Some rationalizing substitutions. Doesn't sound very edifying. Let's see here. So, I'll work some examples for you guys. So basically, what's section 8.6 about? In short, it's more of the same. All right? So let's look at number 1. Well, I say it's more of the same, but that's not quite accurate. So here we go. dx over 1 plus the square root of x. How will we do something like this? Oh, I'm sorry, minus.
Can you make that like square root of 1 minus square root of x and then full and
I think, well, what I'm told here is that I'm looking back in the section, and like he introduces this sort of substitution. Basically, it's a sort of an implicit substitution. So if we let u squared equals to x, that makes what?
1 minus
Is that right? Sorry, just a second. I mean, example 1 in the chapter here, in this section, uses this. So you said it's 1, yeah. So that would make u equal to the square root of x, and it also makes what? 2u du equal to dx, right? So what do we got here? So we've got ourselves a 2u du divided by what? 1 minus u. How would we do that? Now here is a good opportunity for us to use the adding 0 trick. So what this is 2 times, stink. I guess it's meow. Awkward. If you guys don't mind, I'm going to pull a minus outside so I can think more clearly about this one. It's been a long day. With that, I have an easier time thinking. I'm going to leave that minus outside. So look at this. This is 2 times u minus 1, right? Then what? So this is the rationalizing substitution, right? If I do this, what do I it's not done yet, right? To be fair to the step above, what do I have to also do? Right, plus 2. Right. Of course, there's still a du. Don't leave that out. Now, like you said, somebody was saying that cancels, right? Yeah, so we do algebra. This is minus the integral of what? Of 2 plus 2 over u minus 1. That I know how to integrate. So what do I have? I have minus 2u minus 2 times the natural log of the absolute value of u minus 1 plus a constant, or going back to x, we got what? Minus 2 square root of x minus 2 the natural log of the absolute value of the square root of x minus 1 close absolute value plus constant, answer. I'm sorry? I have a log here.
Yeah.
Is okay? Okay. Let's see here. Let's look at let's take number 16 for a spin, see how that goes. There we have integral of dx over 1 plus e to the minus x. Now, you guys, if you don't see, if this adding 0 thing is too mysterious for you, you could also do this, right? So I do 2. I mean, whatever floats your boat. This same song and dance, just different way to do the algebra. Add 0, long division, pick your poison. Okay? Some of you are like, I'll make a w equals 1 minus u substitution and do it that way. Fine, go for it. It's up to you. I mean, there's other ways to do this integral as opposed to do the long division or the adding 0, right? I can make a w equals u minus 1. That will convert the upstairs to a sum, right? But anyway, this one. So I'm going to glance in the section here for a second. This is kind of sort of like example 3. In example 3, what they do is just to set the whole radical equal to u. So I think the analogous substitution here might be, I'm going to try something. We'll see if it works or not, all right? I think maybe if I let u equal to 1 plus e to the minus x, that might do it for us. I don't know. That makes the denominator nicer, right? But what does that say about x? What is x equal to then? Yeah, natural log of u minus 1 equals the natural log of e to the minus. I'm not sure this is good. I mean, I'm not sure yet. This is minus x. So apparently x is equal to minus the natural log of u minus 1. Yeah, I mean, you could put the minus inside, but this also gives us dx is what? So basically minus du over u minus 1. Let's see what happens if we actually do this. So this is going to be the integral, right? And so this is 1 over u. Then times dx. What's dx? Minus du over u minus 1. Let me clean this up just a bit. This is the integral of du over u times 1 minus u. Great, we can do that. We can integrate any rational function of u. We know partial fractions. Right? So how do we do this? U minus 1, 1 minus u. Absorbed it. I absorbed the sign into the denominator, but thank you. All right, so I mean, this is a rationalizing substitution in the sense that we've gone from having some function with exponentials, right, to a rational function in u. So we know how to integrate rational functions, so score. Let's see here. So let's do the algebra. 1 over u times 1 minus u is equal to a over u plus b over 1 minus u for appropriate choices of a and b. This one's simple enough. Some of you probably could figure out what to do here. I'm just going to do the algebra, though. I won't try to be clever. So if we put u equal to 0, if we put u equal to 1, that should pretty much tell us what the coefficients are. Well, that was kind of boring. No. Okay, so a is 1 and b is 1. The algebra is a little bit easier here than the one we had on the quiz. Okay, so sidebar. Let me continue this over here. Equals integral 1 over u plus 1 over 1 minus u du, also known as log u minus the natural log of the absolute value of 1 minus u plus a constant. But what is u? 1 plus e to the minus x. What's 1 minus u? One minus u equals to what? Minus e to the minus x, right? I think we can clean this up just a little bit. How does this simplify? Well, first of all, what's the absolute value of minus e to the minus x? Right, that's just e to the minus x, right? So log of that is just what? Negative x. But there's a minus outside, right? So this whole term simplifies just to x. And 1 plus e to the x, I don't need absolute values there. 1 plus e to the x is clearly positive. There you go. I think I like my answer like that. Let's see here. Let's look at might sting a little bit. Let's do number 28. Here we're faced with well, that's still not quite what oh no, number 30. Number 30 looks pretty awful. Let's do this one. Integral of dx over 5 plus 3 sine x. So for problems that fail to be amenable to our previous techniques, all right? We know how to integrate like sine to the fourth, cosine to the fourth. Like I've got sine squared times cosine, right? I've got integral, anything, there's like a lot of times we can make a u equals sine substitution, u equals cosine substitution. Sometimes we can make a tangent substitution, a secant substitution, right? These are all things we've done to integrate, integrals of trig functions. This is none of those things, right? This is something else. And so to do this, it's helpful to use what's known as the Weierstrauss substitution. So the Weierstrauss substitution is basically based on this little trick right here. What you do is you let u equal to the tangent of x over 2. All right. Now, let's see here if I can. It's been a little while since I've worked out the Weierstrauss substitution. Let me see if I can explain it to you. Right. So we have formulas for sine and cosine. What are the formulas we know? Reminder, little trig reminders here. No, like the double angle formulas. For example, we know, you guys know, sine of 2 theta is what?
2 cosine and sine.
Yeah, 2 cosine theta sine theta, right? What's the formula for cosine 2 theta?
2 cosine minus 2 sine.
How could I figure that out if I'm not sure?
I use the definition of the limit.
You guys are thinking too hard. Just differentiate. Differentiate sine, you get cosine 2 theta, right?
Oh.
Times 2. And over here we get what? 2 cosine squared theta minus 2 sine squared theta. So therefore cosine 2 theta, at least one formula for cosine 2 theta, is simply cosine squared theta minus sine squared theta. Or you could rewrite that as what? Well, sine squared theta is what? It's 1 minus cosine squared theta. So this is really twice cosine squared theta. Minus 1. That's
how.
So here's a popular formula for it. This is a popular formula for this one. How about tangent of 2 theta? See what you can do? You can do 2 cosine theta sine theta divided by 2 cosine squared theta minus 1, among other things, right? Okay, so what we're going to do is basically to let theta equal to x over 2. If you let theta equals to x over 2, what's 2 theta? Yeah, 2 theta is x. So what's this tell us? For example, what is the sine of x equal to?
2 cosine theta sine theta.
Right, which is what?
X over 2, 2 cosine x over 2.
Yeah. Let's see here. A second, I'm not where I need to be yet. On page 432, he gets that sine of x is 2u over 1 plus u squared. Let's see here. Maybe I'm doing this the wrong way. Let's see here. How else could we attack this? So cosine theta, sine theta, right? This is tangent theta, right? So I can draw a triangle, right? This is sine of x is sine of 2 times x over 2, which is why I have this with respect to that theta. So you draw this little triangle here, theta, right? That's tangent. So tangent theta is what is it? It's u is what? We can think of it as opposite over adjacent, right? So I got myself a opposite of u. What's the adjacent side? Use your imagination, there's a 1 here. Over here, square root 1 plus u squared, right? So in view of all that, sine of x is equal to 2 cosine sine, which is actually what? 2u over 1 plus u squared. Because I get square root of 1 plus u squared times square root of 1 plus u squared, there it is. That is, at least that's my explanation for why sine of x is 2u over 1 plus u squared. Okay, so there's one thing. Let's put that in our toolkit for a minute, for a little bit later. And how about cosine x? Well, you can see what cosine of x is in terms of u as well now that we've drawn this triangle and stuff. Cosine of x is what?
1.
Oh, I'm sorry, I'm an idiot. That's not the thing to look at, is it? Cosine of x, right? Sorry, 1 second. Cosine of x is what? Cosine of x is 2 cosine squared theta minus 1, right? That's one way we could look at it.
Maybe the square root of 1 plus u squared.
Or on the bottom, the sine x. Maybe the square root.
There is 2 square roots. There's one from this one and one from that one. So, yeah. Right. Now this cosine theta, cosine squared theta is what? So this is really 2. That's 2 over 1 plus u squared minus 1. So make a common denominator. We get 2 minus 1 plus u squared over 1 plus u squared, which gives us what? That gives us 1 minus u squared over 1 plus u squared. So, in summary, cosine x is equal to 1 minus u squared over 1 plus u squared. This is all from making the substitution u equals tangent x over 2. So what's dx in this wild world of the Weierstrauss substitution? Dx is, of course, secant squared, right? Dx, sorry, I'll get with it eventually here. Differentiate that, you get du equals to 1/2 secant squared x over 2 times dx, right? Which means that dx is what? It's 2 du over cosine squared x over 2. Did I do that right? I don't think I did, because if I solve for dx, I should multiply both sides by cosine squared, right? So I should have 2 cosine squared x over 2 du. But what is cosine squared theta? Cosine squared theta is just 1 over 1 plus u squared. So this is actually equal to 2 du over 1 plus u squared. So there you go. This trifecta of these three things together, this, and this, together form the machine known as the Weierstrauss substitution. We just have to go through this once. Now that we know it, we can apply it to other problems. All right.
How do you spell his name? Weierstrauss?
W-E-I-E-R Strauss. Weierstrauss. Famous 19th century analyst for what it's worth. But so you put that into practice here. What happens? Making this Weierstrauss substitution. What dx is what? Dx is, you see what you got? You got 2 du over 1 plus u squared. That's your dx. Downstairs, what you got? 5 plus 3 times what? What was sine x equal to? 2u over 1 plus u squared. It's ugly, right? But if we multiply the top and the bottom by 1 plus u squared, we'll have a rational function in u. So this is, again, a rationalizing substitution. So this is equal to, like, multiply the top and the bottom by 1 plus u squared. What do you get? Let me put the next step that we're making in red in the previous one so you can kind of follow along here. So what we're going to do is we're going to multiply this whole thing, all right, by 1 plus u squared over 1 plus u squared, okay? That's how I get down here. So upstairs, it's really easy. What happens is what? You just get 2 du. What happens downstairs, though? You get yourself a 5 times 1 plus u squared plus what? This here just is 6u, right? Now it doesn't look too bad, does it? It's not a walk in the park yet, but it's something close. I mean, we can do that. We can do this integral. We just need to clean up a little bit. What is this really? We got ourselves a 2 du over 5u squared plus 6u plus 5. I copied this problem out of the 10th edition of a relatively venerable textbook. The odds are pretty good that this is not an ugly quadratic. Can you factor that? In other words, is this 5u times something plus u times something else? Factors of that are 5 and 1, right? Ah, my faith in the book is shaken. This problem is uglier.
Can't you like split it up and do it where it's like 1u plus 5u plus 5 and like...
No, you can't. This dog, to quote my community college professor, will not hunt. This is in fact not the truth. This is what Dr. Sprano would call bad algebra. No. Okay. We cannot do that. No solution. All right, so what does that mean we're facing? That's what I was about to say. But now you know that because you completed the square?
Oh, no, I take it.
Discriminant, okay. So we can complete the square here. It's just a little bit of a drag. So this is the integral. I can factor a 5 out basically, right? 1/5. We're going to have to deal with some fractions here, but it won't kill us. U squared plus 6 over 5 times u plus 1. Now, I'm going to work on that quadratic over here. So u squared plus 6 over 5 times u plus 1 is equal to u plus 3 over 5 quantity squared. I'm completing this square. I took half of the middle term and I added it to u. Squared it. That effectively adds 9/25. But I only had 1 to start with, right? So I have to subtract 9/25 from 1 to be fair. In other words, I have to subtract 9/25 from 25/25. AKA 16/25. Woohoo! So this is 1 minus 9/25 is 16/25, which is actually pretty nice because, yeah, this squares. So this is really 1/5 integral of 2 du over u plus 3/5. My faith in the book is restored. 3/5 squared plus 4 over 5 quantity squared. And that I can do making however you want to look at it. This is basically a tangent substitution. Can I just write down the integral at this point? I mean, I can. Maybe I better do some work for you. So we let u plus 3/5 equal to 2/5, 2 over 5 tangent. I have not used theta yet, except over here. I don't want to confuse that theta with this theta, so I better make it a different angle. Let's call it tangent beta, as to not confuse with the theta. I'm making a new variable beta to do this integral. If with this substitution, u plus 3/5 squared plus 4/5 squared is actually going to equal to 16 over 25 secant squared beta. And on the flip side, du is going to equal 2/5 secant squared beta, d beta. So if you make this red substitution, the secant squareds cancel. All right, so we've got 1/5. I'll write it out though. So that's 2. My du is 2/5 secant squared beta d beta. Downstairs, I've got a 16/25 secant squared beta. The wonderful thing here, of course, is the secant squareds cancel by proper sound effects. And then some other things cancel, right? Like, oh yeah, check it out. So this 2/5 comes out in here and makes a 4/25, but when you multiply 4/25 by that, 25s cancel, and you're left with 4 over 16, so it's 1/4. So I've got 1/4 integral of d beta. Which we can do, right? So that gives you a beta over 4 plus a constant, which gives you 1/4 inverse tangent of u plus 3 over 5 plus a constant. At this point, I have to undo the u. What did it make u? U was what? Tangent x over 2. And so there it is. Our answer is 1/4 inverse tangent of u. What u was the tangent of x over 2. Plus 3/5 plus a constant.
I think you actually made an error that would better result.
Really?
When you were squaring
Oh no.
the 2/5 tangent.
I sure hope you're wrong. Where did I make my error?
The red stuff on the side is 2/5, and then you went down. And you went from 2/5 to 16/25. Oh, but then you added. Okay. No, I think you're right. You squared it and you added 16/25.
Yeah, this right here is because tangent squared plus 1 is secant squared, and there's a 16 over 25 which rides along. Oh,
But you had a 2.
4 over 25.
Yeah, it should be 4 over 25. So basically everything was multiplied by 4.
4 over 24. No, it should be 16 over 25. So the point is,
Oh, so it was right.
so this should have been 4 over 5, right? My red substitution's like a little bit off. Let me fix it in blue. Yeah, you guys should have stopped me.
It took me a while to decide.
Ah. Excuses. All right, 4 over 5 is what I should have made the substitution, right? That has a few wrinkles. Basically, that puts a 4 here, right? Where else does it put a 4? This is fine. That was a correcting mistake. So basically, the place where that 4 appeared was here. And so that would give me an 8 where I before had basically I just multiplied my answer by 2. So I think that just ends up, that just makes it a 2 instead of a 4 there. Thank you. Much appreciated. No, 3 over 5.
I mean, the tangent beta is equal to, supposed to be equal to 5u because 3.
Oh, you are right. My, thank you. See, I did the Weierstrauss thing correctly, which is like really the hard part, and then I'm just messing up this silly stuff at the end. I am so sorry about this. So, this means that tangent beta is what? 5 over 4, right? Times u plus 3 over 5. Solving for tangent beta, I have to multiply both sides by 5/4. I neglected to think about that. And so I should have not inverse tangent of this. I should have inverse tangent of that, 5/4 of u plus 3/5. Of course, you can multiply that through and rewrite it if you wanted a little bit differently. That's also over here, of course. There's a 5/4 here that I was neglecting. Have we found all of my sins? Do I have more? Is there more? I mean, this is a hard problem, right? Yeah. So as a matter of common human decency, if I ask a Weierstrauss problem on a test, I provide for you, first of all, a suggestion that you use the Weierstrauss substitution. Second of all, this, and that. Right? Basically, the definition of the substitution, as well as the sine x, cosine x, and dx formula we derived. All right. So if I do assign a Weierstrauss substitution, it comes with like a lot of goodies. It's still a pain in the butt. Yep.
Sorry.
Oh, you're just stretching? Cool.
Will you give us one hard?
Check this out though. Like integral of, say, sine x minus 3 cosine x over, I don't know, 2 sine x minus 7 cosine x, plus 7 cosine x, I'm sorry, excuse me, what was I thinking? Dx. That's kind of awful, right? But you just make a Weierstrauss substitution, and it becomes awful, but a different sort of awful. It's sort of awful that it's just a matter of perseverance on your part. What's that? Oh, yeah, see, I'll do that again. Ow. So the point is, that's a rational function in U. Partial fractions is totally general. It's awful, but you can do that integral. And so I've just showed you a technique, right, which if you have sufficient courage, or somebody pays you money, or some combination thereof, you can integrate any rational function of sine and cosine. So I take any fraction linear combination, like sum of sines, sum of cosines, upstairs and downstairs. I can convert it to a rational function in U, partial fractions, integrate it, done. But I'm not going to do another example. I think that's enough. We have suffered enough. In your homework, I have recommended a problem which has the hyperbolic analog of this. And if you look at the solution, I have derived sort of the hyperbolic Weierstrauss substitution. There's also one of those for doing the same thing, but with cinches and coches. That also exists. Anyway, let me try to work another example here that is not one of these. Wait a minute. Are we out? Oh, all right. Well, it was fun. Tomorrow, numerical integration. Woohoo!